So something as everyday as a tossed object into the air has a quadratic relationship between the height of that object and the time that has gone by. So h is height of the ball, t is the point in time since the ball was thrown up into the air, and then v sub 0 or v naught is the speed at which that ball is thrown skyward. So if you're in physics with me, you'll see that this is quite familiar looking. It is basically our one of our kinematics equations. And you can tell that this is in feet, because that is the acceleration of gravity in feet per second, 32, divided by 2, or 16. And then just rearranged so that, oops, forgot our square term, so that the square term for time is in the front, kind of our standard format. Alright, so we can look at a couple of interesting questions that I've listed here. This is a problem in your book, page 57, number 129. We'd like to know, hey, what time, how many seconds have gone by when the ball is 20 feet up in the air? At what time t does h equal 48? And then here's where we're going to use the discriminant. What is the maximum height? We can actually find out what the height is at the very top, right? Because that's going to be our one solution situation. What is the time when the ball reaches the top? And then when does the ball hit the ground? Which, as you might surmise, has two solutions. One, the ball is at the ground when it is launched, and it returns to the ground at a second time t, which makes sense, right? Most of the time when you solve for a variable that is squared, you'll get two solutions. So we'll simply see which one makes the most sense in terms of when the ball returns to the ground. So for the first part, we simply solve for when does the height equal 24. So we'll substitute 24 for height, and then everything else is the same. So I'm going to subtract 24 from both sides so that we have this in our standard form. I forgot to write over here, these assume that initial velocity is 40 feet per second. So that's 40t minus 24. Looks like we have a common factor of -8. So the nice thing about an equation, we don't even need to factor it out, we can just divide it out. And then I'll put the 0 on the other side. Alright. This one factors nicely, it looks like. Turn it into, oh, wait a minute. Are my signs correct? Looks like we can factor this by grouping. So 2 times 3 is 6. And 6 we could split into 6 and 1, but they're going to be the same sign. So really we should do 2 and 3. They multiply to 6. Looks like we need -5. So these multiply to +6 and add up to -5. So 2t squared minus 2t minus 3t, split those up, and factor out 2t, t minus 1 plus, minus 3t minus 1. Okay, so that will give us this above, and we'll factor out t minus 1, and this is equal to 0 as above. So either t equals 1, or if 2t minus 3 equals 0, 2t equals 3, and t equals 3 over 2. Okay, so looks like two solutions. If that's time and that's height, basically it looks like at 1 second and at 1.5 seconds it reaches a height of 24 feet, is the way that we could picture what is going on here. Okay, so that's how we would solve for time when height is 24. Well, what about this next one? When is the height equal to 48? We could do that over here. Let's say 48. It's going to be very similar. Plus 40t. If we arrange as we did before, we'll have negative 16t squared plus 40t minus 48 equals 0. We can divide through by negative 8 again. And we have 2t squared minus 5t plus 6 equals 0. So now we're looking for factors of 12 that add up to negative 5, which I don't see. Well, let's check and see if this is possible before we go through the process of completing the square. So our first use of the discriminant, let's compare b squared, which is 25, and then 4ac. ac is 12. 4 is 4. Oh, looks like 4ac is bigger, which means that this is going to be less than 0, which means the discriminant is less than 0, which means that the square root of that is imaginary, and therefore this actually has no solution. In other words, 48 is up here, 48 feet, and our ball never reaches 48. I don't know where this is. That's the next part. What is the maximum? But clearly, if this has no solution, there is never a time at which the height is 48, which in in the real life situation, the ball never reaches 48. So where does it reach to? What is my maximum height? Well, for that, we will leave h as our unknown. Okay, so we still need to set this into equals, something equals 0 form, so we'll do that. Minus h equals 0. Alright, in this case, a is negative 16. So we're going to look at the discriminant. Alright, we're going to take a look at the discriminant. B is 40, c is negative h, and so b squared minus 4ac. And the idea here is that at that maximum h, maximum height, this is where the discriminant is equal to 0. So we know a and b. What we're looking for is, hey, what value of h causes that expression to equal 0? What value of h? Well, we know everything else except for c, or negative h, so we can solve. 40 squared is 1600 minus 4 times negative 16 times negative h, which is 1600. We've got 3 negative signs, so that'll be minus 4 times 16, 64h. Alright, that is the value of my discriminant for whatever value of h, so I'm looking for the specific value of h where the discriminant is equal to 0, because that is our one solution That's our one solution value of h. So that would be the maximum height. So we just solved this for h. Add 64h to both sides. Divide by 64. And we have h is equal to, let's see, I can divide by 16. Oh, 25. H is equal to 25. That is my maximum height. And that kind of makes sense looking at the picture up here. Alright. So maximum height is 25 feet. At what time? At what time is h equal to 25? Well, let's see. We could go back to the original formula, plug in 25 for the height and solve for t. Since we've done the discriminant, we're kind of almost there already over here, because the solution to this, we've already identified a, b, and c. We can, in a sense, use the quadratic formula, since we're nearly there already, and we already know that the discriminant is 0, so that saves us a whole bunch of work. We can just plug in, right, because normally the solution to this is the values of x, so here t is our square second degree variable, which normally is x if you're thinking about a standard quadratic. So our solutions for t, or in this case the one solution, will be negative b, which is negative 40, plus or minus this we already figured out is 0 when h is 25. Then we just divide by 2a, which is negative 32. Our negatives cancel. That looks like 1 and 8 over 32, or 1 and a quarter seconds. Okay. And going back to our picture, indeed that makes sense. That is halfway between the two solutions we found for A. So that makes a lot of sense. And then when does it come back to the ground again? It's something we can actually do pictorially, but since we're practicing with this equation solving, we will do that here. And then I'll show you how you could do that visually. So height is equal to 0, negative 16t squared plus 40t. We can go ahead and divide by negative 8 on both sides again. Okay, and then here actually we can go ahead and factor this, right? We can use 0 product property, I think. We can take out 2t and be left with t minus 5 over 2 is equal to 0, and I flip them just because I'm used to having 0 on the right. So there's my 2t squared, and there's my 10 over 2, which is minus 5t. Alright, so here t is either equal to 0, which is actually here, right? So you can't see that. Here. Time equals 0, height equals 0, because it's being tossed up from the ground at that point. Or 5 over 2 would make this 0, 2.5 seconds. Alright, so this one makes sense for return to the ground. Those of you in physics remember that this is a symmetrical curve, and so you could even look, well, 1 second to reach 24 feet, a half a second comes back to 24 feet, and this length is going to be the same as this time, so I just add 1 second, and I know this is not to scale, but this would be the same 1 second returning from 24 feet, because these are symmetrical. So that's the other way that you could do it.